Section 7.4, Rational Exponents. Here we have a definition of a rational exponent. If the nth root of a is a real number and m is an integer, then I can write a notation of our radical. Here we have our radical as we've seen in previous sections. I have an index of n, our radical symbol, and our radicand. We can now, with the definition of the rational exponents, write our radicand with a fractional exponent in such a way that the denominator is the index of my radical and the exponent on my radicand is in the numerator. Therefore, I have my radicand a, which is to our first power, and nth root, a to the 1 over n. I also can do that in such a way if I have a radical of an index of n and also have an integer of m that is greater than 1 or less than 1 if it would be negative. Here, I would have my radicand a to the m over n power. Again, the exponent of my radicand and the index of my radical. I also can take my exponent out and solve for the nth root of my radicand and then take the exponent of the solution. Either way is acceptable. I must keep in mind that if my m, or exponent on my radicand, is negative, that would take my radical to the denominator. If that is the case, I would not allow to have a to be 0 because that would make my fraction undefined. Let's look at some examples. Here I want to convert to radical form. If this is true, I know that this is my n, which is my index, and my m is the exponent on my radicand. So what I'll have is the cube root of x to the 4th, which I also can write as the cube root of x to the 4th power. On this example, I have z to the negative 1/6. Since I have a negative exponent, I need to take this term to the denominator. Therefore, that gives me z to the positive 1/6. And that leaves me with a 1 in the numerator. Now I can convert this to a radical form, which is 1 over the 6th root of z. Of course, I should simplify that further and rationalize, but here that's not what they're asking for. We just want to write this as a radical. So this would be 1 over the 6th root of z. And the exponent of 1 is in the interior. On these examples, I want to write the radical expression in exponential form. Here I have the square root of x cubed. This is my nth degree. This is my exponent for m. Therefore, my radicand, which is x, m over n, is going to give me 3 over 2, x to the 3 halves. I can rewrite this as the 5th root of x cubed. 5 is my n, 3 is my m, or x to the 3/5. Here I have a negative 2. I can rewrite this as the 7th root of x cubed. Now I can convert this to an exponent, which is a negative 2 over x to the 3/7. Then I could write this term in the numerator, which would be a negative 2 x to the negative 3 over 7. On the next 2 slides, I have the properties of rational exponents. I'm going to review them quickly, but you can always pause the video and review them at your own pace. Here, I have multiplying of like bases. When we multiply like bases, we add our exponents. And of course, we have samples for each. Here, I have a power taken to a power. When that occurs, I will multiply the exponents. When I have a set of parentheses with an exponent on the exterior, remember that that exponent must multiply each term on the interior. Continuing, if I have a negative exponent, remember I have to take that to the bottom. If it happens to be negative on the bottom, I will move it to the top of the fraction. Here, if I have like bases and I want to simplify, therefore I will subtract the exponents, the top exponent minus the bottom exponent. And again, if I have an exponent outside of a set of parentheses, that exponent will go to each term in the numerator and each term in the denominator. Here I want to simplify each expression. Whether I need to rewrite that is up to you. If you want, I could rewrite this as the square root of 49, which I know is going to be 7, or plus and minus 7. Here I have the fourth root of 16. And we know the fourth root of 16 is 2. Here I have the square root of x to the fifth. And I can simplify this by writing x to the fourth times x. Because, like bases, I add the exponents. 4 plus 1 is 5. Now I can take the square root of x to the fourth, which I know to be x squared, leaving me this x under the radical. Here I want to simplify each expression. Here I have 4 to the 1/4 times 4 to the 1/4 times 4 to the 1/4 times 4 to the 1/4. All have like bases. I'm going to rewrite the base, add their exponents. 1/4 plus 1/4 plus 1/4 plus 1/4 is 4/4, which is 1. Therefore, my solution is just 4. 4 to the first power. Again, I want to multiply, and I have like bases. I'm going to rewrite my like base, which is a negative 16, and add my exponents, which are going to be 1/2 plus 1/2, which is 1. Negative 16 to the first power, or just a negative 16. Here I have 36 over 121. I want to take that to the 1/2 power, which is really the square root of 36 over 121. The square root of 36 is 6. Square root of 121 is 11. Here I have 49 to the 1.5 power. That can be written as 49, and write this as a fraction, to the 3/2 power, which I know can be written as the square root of 49 cubed, which can be written as the square root of 49, and then that would be cubed. It's easier to solve this one rather than to cube 49. Therefore, I'm going to take the square root of 49, which is 7, and take 7 cubed, 343. In this example, I have 16 to the negative 3/4. Since my exponent is negative, I need to take that to the bottom. I'll have a 1 in the numerator, and that will be the fourth root of 16 to the third, which I can rewrite as 1 over the fourth root of 16, and I can set that in parentheses, and I can cube that quantity, which will make it easier when I want to simplify. That'll be 1 over the fourth root of 16 I know is 2, and that's 2 cubed, and that, when I multiply, is going to be 1 over 8. I could have simplified here by taking the cube of 16 and then taking the fourth root, but it's easier to follow this method. Here I have 81 to the negative 0.5 power. My exponent is negative, therefore 81 will go into the denominator, leaving 1 on top. My exponent will become positive when I drop 81 to the denominator, and 0.5 is going to give me 1/2. Or I could write that as a radical, which is the square root of 81. Then I can simplify, and I get 1/9. Here I want to write each expression in simplest form. I have 3 over x to the fifth, and that quantity is to the negative 5th power. Therefore, I can have 3 over a power taken to a power is going to give me x to the negative 25th. But since my exponent is negative, I need to rewrite that term in the numerator, which is 3x. And since I moved it to the numerator, a positive 25. 3x to the 25th. Here I have a quantity that is to the 1/2 power. What I want to do first is to simplify inside my quantity. Therefore, I'm going to use the quotient rule on my exponents, and I'm going to have x, top exponent minus the bottom exponent. 5 minus 3 is 2. And y, 6 minus a negative 2, which is 6 plus 2, which is 8. And that is to the 1/2 power. I can rewrite that as a radical, which is the square root of x squared, y to the 8th. And I can simplify. The square root of x squared is x. The square root of y to the 8th is y to the 4th. Again, I want to write each expression in simplest form. Here I have the quotient of y to the 5/6 over x to the 2/3, all taken to the negative 12th power. I'd like to simplify inside my quotient, but my bases are not like, therefore I cannot apply any of my properties. But what I can do is go power to the power with the exponent in the numerator and denominator, or in other words, multiplying each times a negative 12. Therefore, y, 5/6 times a negative 12 is going to give me a negative 10 over x, 2/3 times a negative 12 will give me a negative 8. Since these have negative exponents, I need to take their base and move them to the numerator and denominator. That gives me x to the 8th over y to the 10th. Again, I want to simplify the expression. Here I can choose to either multiply inside my parentheses or use power to the power. What I'm going to do is to multiply inside my parentheses. That's going to give me 81 times 1 is 81. X to the 1/2 times x to the 5/12. So I add their exponents. Common denominator is going to be 12. Multiplying the top and bottom by 6 gives me 6/12 plus 5/12, which is 11/12 to the 1/2 power divided by x to the 3/4. Now I choose to do the power to the power, which I need to do. That's going to give me 81 to the 1/2 power. 1 times 1/2 gives me the 1/2. And x to the 11/24 power. 1/2 times 11/12 is 11/24. And then I can put my x to the 3/4 on the denominator of that expression. This symbol and this symbol represent the same operation, which is division. I know that 81 to the 1/2 is the square root of 81, which is 9. And I need to simplify my variables. And since this is a quotient of these two and they have common terms, I need to subtract my exponents. To do that, I need common denominators for the fractions. That's x to the 11/24 over x, and changing this to a denominator of 24 multiplied by 6 gives me 18/24. Now I subtract. That's going to give me 9. X 11 minus 18 is a negative 7/24. But since the exponent on my x is negative, I need to take that to the denominator. Therefore, my solution is 9 over x to the 7/24. Again, I'm going to simplify this expression. I have a expression taken to a power, taken to a power. So I want to work on the inside out. So what I want to do is take the power to the power of the 1/3 with this expression, leaving the 1/2. So I'm going to put my bracket down for the 1/2 power. I'll take care of that later. Here I'm going to have 64, which is to the first power. 1 times 1/3 is 1/3. X, negative 2 times 1/3 is a negative 2/3. I can simplify, and I know that 64 to the 1/3 is the cube root of 64, which I know is 4. X to the negative 2/3, and that is all taken to the 1/2 power. Now I need to power to power again. That's going to give me 4. Its exponent is 1 times the 1/2 is 4 to the 1/2 power. X, a negative 2/3 times a positive 1/2 is a negative 1/3. This is the square root of 4, which I know is 2. And since x has a negative exponent, that needs to go to the denominator, which is x to the 1/3. I could rewrite that as 2 over the cube root of x, but this is fine. Again, I want to simplify. I want to change these to rational exponents. So that's going to be, when I do that, rewrite everything else. And this is going to be x to the 5/2 and y to the 5/2. And that's all going to be taken to the 1/3 power. Now, I can use my power to the power rule, which gives me x to the 5/6 times y to the 5/6. And that is all to the negative 1/5 power. Now I use power to the power again. That is going to give me x. 5/6 times a negative 1/5 is going to give me a negative 1/6. Y, 5/6 times a negative 1/5 is a negative 1/6. Since these are both negative, they need to go in the denominator, which is 1 over x to the 1/6, y to the 1/6, which can be written as 1 over the 6th root of x, y. To simplify this expression, I'm going to do the power to the power rule first. Whether this is a numerator and denominator or written in this fashion, I know that 12 has to be multiplied to each exponent of each term. So this is going to give me x. 1/2 times 12 is 6. Y, a negative 2/3 times 12 is a negative 8, divided by x. 3/4 times 12 is 9, and y, 1/2 times 12 is 6. Then I can write that as a quotient to help out. X to the 6th, y to the negative 8, over x to the 9th, and y to the 6th. Now I can apply the quotient property to my exponents, which means I subtract the exponents, the top minus the bottom, and rewrite it on the numerator, then decide if it's positive or negative. So therefore, my x, 6 minus 9 is a negative 3. It goes to the numerator. We decide if it drops, if it's a negative later on. Y, negative 8 minus 6 is a negative 14. These exponents are both negative, therefore we'll put them in the denominator. X to the 3rd, y to the 14th, and since there's nothing in the numerator, I must put a 1. Here, power to the power, 5. Square root of 2 times the square root of 2 is the square root of 4. The square root of 4 is 2, and my solution is 25. Recall, when I multiply like bases, I add their exponents. If I don't have like bases, I can just leave them as a product. But the thing is, I can make this a like base. In other words, I can write 49 as 7 squared. And then that would go along with it, which would be a negative 2 square roots of 2 times 7 to the 2 square roots of 2 power. Now I have like bases. So I can rewrite my base and then add my exponents. A negative 2 square roots of 2 plus 2 square roots of 2. Since these are like terms, they will combine and get 0. Of course, we know anything to the 0 power is 1. Here, I have a quotient property I'm going to do with my exponents. Rewrite the base, which is y. Subtract my exponents. 10x minus 4x is 6x. And I have 4 y to the 2/3, all taken to the negative 1 power. Since this quantity is all taken to the negative 1 power, that means this all has to go to the denominator. Or I could use the power to the power rule, which would be 4 to the negative 1 and y to the negative 2/3, which would also tell me that this has to go to the denominator, leaving me with a numerator of 1.